Hello students, this is Professor Chalai, and in this video we're going to look at significant figures in measurement. As always, you can follow along with our chapter 1 worksheets. Now, so far we've looked at measured numbers, and we talked about how there are two parts to a number. There is the actual number itself. Let's say in this case we're measuring a volume and we got a value of 13.52, and then there are the units. In this case, if we're measuring volume, maybe the units are in milliliters. There is a third aspect to measured values that we haven't talked much about so far, and it's a measurement of uh, the uncertainty of the number. Because every value that you've measured will have some uncertainty. Well, most values that you measure will have some uncertainty to it. So how do we represent uncertainty in a measured value? We already have the number and the units. How do we represent the uncertainty? Well, we represent the uncertainty using significant figures. Significant figures, or sig figs for short. And how do we represent the uncertainty in significant figures when we're measuring values? Well, let's look at an example. In chemistry laboratories, you're going to be using glasswares a lot that usually have markings like these that tell us what the values are. So in this example, this is going to all be in milliliters. And we see that our measured value lies somewhere between 13 and 14 milliliters in this example shown right here. So let's zoom in a little bit more. We have 13 milliliters on the bottom, 14 milliliters on top. So that means that every one of these markings, there are 5 spacings. So every one of these are going to be 2 milliliters. So that's 13.2, 13.4, 13.6, and 13.8, and then 14 milliliters. Okay. We see that the bottom of our meniscus, and that's where we need to take our measurement, usually for aqueous solutions, there's going to be a slight dip downwards. Aqueous solutions just mean solutions involving water. There's going to be a slight dip downward, and so we're going to have to look at where the bottom of that downward dip is, and that's the bottom of the meniscus. Let's just write that, meniscus. I spelled that wrong. There we go. So the curve is called the meniscus, and we want to measure the bottom of it. In this case, it happens to fall somewhere between 13.4 and 13.6 milliliters. Well, we need to make a guess because there are no markings in there, but we know it's not 13.4. We know it's not 13.6. So we need to make a guess as to what it is exactly. And in making a guess, we're basically guessing the last digit, one digit further than the instrument actually gives us. In this example, it looks like it's a little bit more than halfway through. Halfway through would be 13.50 milliliters. So I'm going to guess 13.52 milliliters. And that's how I arrived at this number right here, 13.52 milliliters. So in this example, we know that we have about 13.52 milliliters of solution. The significant figures here, specifically to 2 decimal places, gives us a measurement of how uncertain our values are. We know for sure then that we don't really have 13.521 milliliters because that one doesn't really mean anything. Our instrument could not possibly give us an estimate for that digit. Okay. So that's where uncertainty comes from. Usually comes from a limitation of our instruments, and we represent those uncertainty by the number of significant figures that we record. If we had recorded 13.4 or 13.6, that would also not be accurate because we know it's not, our instrument tells us it's not really one of those, it's somewhere in between. All right, so there are a few ways to represent significant figures when you're writing numbers. And I'll go over them one by one, though you may be familiar with some of these. First and foremost, all digits that are not 0 are going to be significant. Doesn't matter where they appear, in the beginning, at the end, in the middle. If they're not 0, they're going to be significant. An example here is just the 5 and the 4 in this number, 0.0540. The second So every other rule then has to deal with how we treat zeros in significant digits. So let's deal with them one by one. So let's look at captive zeros, and those are zeros in between other numbers. And if your zeros are between other numbers, they're captive between those other numbers, they're always going to be significant. So the 7.003, those zeros are between significant numbers, so they're also going to be significant. So in the first example, we have 5 and 4, so we have 2 sig figs. I'm just going to shorten this to SF for now. In the second example, the zeros are also significant. So we have 1, 2, 3, 4, 5, 6 sig figs. So these have 6 sig figs. Let's look at other cases. Let's look at leading zeros. Leading zeros are not significant. So leading means they come to the left of the number. Let's look at an example over here. These zeros are all leading. They're to the left of the number, so they're not significant. So in this example, we only have one significant figure. Similarly, if we have something like 001, right? Might as well just write 1 because those zeros are not significant. We only had one significant figure, so might as well just write 1. So leading zeros, not significant. Trailing zeros, so those are trailing zeros towards the right of any number. Those cases are a little bit more iffy. So let's look at them one by one. If it's after a decimal point, they're significant. So in this example, we have 1, 2, 3, 4, 5 significant figures. If they're before a decimal point, they're also significant. So if you have a decimal point here and they're between a real number and that decimal point, then they are significant. So in this example, there are going to be 3 sig figs because those zeros are between a decimal point and a significant digit, 1. However, if they are before an implied decimal point, meaning that you didn't actually write the decimal point there, then they're not significant. So if you didn't put the decimal point there, that's what we call an implied decimal point. We know that there's a decimal point there, but we actually didn't write it. Then those digits automatically become not significant. So in this example, there's only one significant digit. So that's a good way to think about to use decimal points. If you wanted to write 10 and show that it has 2 significant figures, you just put a decimal point there. If you wanted to write 100 but show that it has 3 significant figures, you do 100 decimal point. If you wanted to write 100 but show that it only has 2 significant figures, it's a little bit more tricky. So 100, but how do you show that it has 2 significant figures? If you put a decimal point, it becomes 3 significant figures. That's where scientific notation comes in. 1.0, that has 2 significant figures, times 10 to the 3. So here, this is 100, times 10 to the 2, second power for 100. That shows that it has 2 significant figures. So that's how you use scientific notations for tricky numbers. Okay, so this is how we recognize significant figures. The other thing that I want to mention is not all figures that you measure is going to have some sort of uncertainty associated with it. Most will, but not all will. For example, if I were to ask you how many people are in the room with you right now, the answer could be 0 or 1 person, or I don't know, maybe there's 100 people in the room with you. Not advisable during COVID, but that's okay. Really, we can't have 0.1 person in the room with you. We're not counting people standing halfway between the door. So the number of people in the room with you is going to be an exact number. It's going to be either 0 or 1 or 2. We can't have 1.0000001 person in the room with you. So in those cases, numbers like whole numbers that are counting something usually are what we call exact numbers. So exact numbers you can think of it as having no significant or an infinite number of significant figures. There we go. So, if there's one person in the room with you, it's exactly the same as saying there's 1.000000000 forever persons in the room with you. So that's going to be useful in calculations later on to think of exact numbers as having an infinite number of significant figures. Earlier we talked about unit conversions, and I said that 1 inch is equal to 2.54 centimeters exactly. What I meant by saying that is 1 inch is equal to 2.54000000 forever by definition centimeters. And so if we need to think about significant figures, we just have that in our mind that it's exact. It's the same for conversions in metric scales. For example, 1,000 meters is 1 kilometer. I haven't said it, but that's an exact conversion. Like there is no like 1,000.0001 meter is a kilometer. Doesn't work that way. It's an exact conversion. 1,000 meters is a kilometer. That's exact, meaning we might as well write 1,000.0000 forever meters is equal to 1 km. We don't write it because it doesn't add anything, the extra zeros. So we just say that those conversions, those values are exact. And keep that in mind for when we do significant figures in calculations. Okay, with that, I'd like you to just spend some time and answer number 22. You can pause the video here, answer number 22, and when we come back, I'll just go over some of these with you. Okay, so number 22 asks, how many significant figures are in each of the following? The first one is 0.02344, 0. So let's look at these. We know that all of the non-zero digits are going to be significant. We know that leading zeros are not going to be significant, but we know that trailing zeros, especially after a decimal point, are going to be significant. So in this example right here, there are 4 significant figures or digits. Let's do another one. Let's do C. 1, 0, the 1 is significant. This trailing 0, there is no decimal point. It's not after a decimal point, so it's not significant. So this gives us 1 significant figure. The 10 over here, though, there's a decimal point right there, so that gives us 2 significant figures. Let's look at the scientific notation. 1.00, these zeros are after a decimal point, so that gives us 3 significant figures. Remember, look, just note that I don't really consider the little factor right there, 10 to the second power. F. These zeros are all leading, right? They come before anything else, so they're not significant. So this is 1 significant figure. In 10,000 over here, these zeros, there's no decimal point, they're trailing, so we also have 1 significant figure. And over here, another scientific notation, we only look at the first part, and it's 1.0. This 0 is after a decimal point, so it's 1 significant figure. Okay, try number 23 for rounding. So in rounding, if the number is 5 or above, so I'm going to write this just slightly different from your textbook. Just to make it, I'm going to make it easier than your textbook has. The rule is if the next number that we're going to be rounding from, let's just put next number, is 4 or below, keep the digit. And if the next number is 5 or above, round up. That's it. We're going to keep it simple. I know your textbook has a little bit more complicated rounding rules, but that's it. If the number is 4 or below, we keep the digit that we're rounding. If it's 5 or above, we round up. So spend some time, do number 23, pause the video, and when you're done, you can unpause and we'll go over some of these. Okay, 23.A, we have 0.424 to 2 significant figures. So two significant figures. So we're looking at this number right here. It's 4. So we keep the number that we don't round up. We keep the number as is. So it's 0.24, and we just drop the last 4 because we need to round to 2 sig figs. Okay. In B, we're rounding to 3 significant figures. So we have 1, 2, 3. The next digit is more than 5 or more. So we round up. So we end up with 0.00387 because this 6 gets rounded up. For C, let's look at C. 421.25 to 4 significant figures, so that'll put us at 1, 2, 3, 4. So we look at this digit, it's a 5. So we round the 2 up. So 4.213. Sorry, not 4.213, but rather 421.3. And finally, 28,683.5 to 5 significant figures, 1, 2, 3, 4, 5. This number is 5 or more, so we round the 3 up. We get 28684. All right, so that'll do for significant figures and how to count them and how where they come from in terms of measurements. In our next video, we're going to actually look at how to use significant figures in calculations. I will see you in the next video.